I'm now recording, and you guys should see that I'm recording. Do y'all see a little message on your screen?
Yes, ma'am. Yes, ma'am.
Can y'all read? Is my writing backwards for y'all?
No.
Okay, I guess it's just because it's my camera. Okay. I guess it's just because I'm viewing my own stuff, it's backwards. All right. Now, I saw Tony come in. I did not see Quenisha. Okay. So I am recording. So the recording will show up on Canvas. Obviously, it won't be on the conferences. I'll probably just put that in an announcement. I've actually never uploaded a Zoom recording, but maybe I'll put it on. I'll figure it out. Y'all know what I'm doing. I'll tell you. I'll tell y'all when I figure it out, okay? Sound fair? Lab Monday, for the group that came to lab on Monday, it was a long lab. Yes. For y'all that were here, it was kind of intense.
It was like 2 hours.
Yes, it was 2 hours. So it is, I wanted us to try to do, I had a lot for that first lab because I had to split y'all up. So it is definitely a 2-hour lab. I do think that the lab helps with intermolecular forces and understanding that. What about you guys that were here Monday? Did it help with intermolecular forces? Actually seeing some of what was going on?
Yeah, a little bit.
Yes, it helps some.
Okay. Okay. Part of what we're going to talk about today will explain some of the stuff you guys observed in lab a little bit more. So those of you who did not come to lab on Monday, hopefully y'all worked on the virtual lab, Avogadro's law and Boyle's law. And I say it over and over and over. Lab is supposed to meet Monday at 12:30, so you should discipline yourself Monday at 12:30 to do your virtual lab. Now you could still do it if you wanted to, but don't put it off. So the other group that was in here with me Monday, y'all can wait till next Monday to do those two, or you could still work on them ahead of time now if you wanted to as well. So I'm gonna put all of you on the spot. Did anybody complete the lab? Did that go okay? How are we there? The Avogadro's law or Boyle's law?
I have a question about that, Ms. Hurd.
Okay.
Like for virtual lab today, for the like group A for virtual lab, are we doing 2 labs today?
No, lab only meets for Chem 2. Lab only meets Monday from 12:30 to 2:30.
Okay. Okay.
So, but Tony, you came this past Monday.
Yes, ma'am. I have a question about the lab that is like our virtual lab for today. Like, no, is it?
Your virtual lab is for next Monday. Lab meets on
Monday. Oh, okay. Okay.
But did you still have a question on it or?
No, ma'am.
Okay. Anything else, y'all? Because I know sometimes on this it's hard. You start talking over somebody and you'll unmute and mute, but that's okay. Was there anything else that somebody had or?
Oh, I just said both already.
I saw Celia. Go ahead, Celia.
Oh, I just said I did them both already.
Okay. And that went okay? I didn't look at grades. I have no idea. Is everything okay? And
yes.
Okay. All right. And Brianna, were you going to say something too?
No, ma'am. I was just saying I didn't have any questions.
Okay. Okay. That's fine. That's fine. So Connect is coming okay. I know Derek, you had emailed me a Connect question, and I'm going to kind of talk about that here. Derek was working on the Chapter 11 Connect. and I can't remember the exact question, but it would give two things. Like the one he had a question on, it told him, all right, you've got hydrofluoric acid, it said HF, and you've got cesium iodide, CSI. It gave the formulas for them. And the question was about, like, when these mix, what forces have to be overcome for these to mix? Because what you've got here is you got a whole bunch of HF in one beaker, right? And you've got whatever forces exist between all these HF molecules. And then in another beaker, you've got a whole bunch of CSI, and you've got a bunch of whatever these forces are between all these molecules. And so in order for these two to mix, you've got to break the forces amongst the HF, right? Intermolecular forces. You've got to disrupt the forces amongst the CSI so that these will mix and be like HF. I'm going to put that in parentheses. And I'm having trouble talking and writing. And see, do you see what by mixing? So what forces does HF have? What type of intermolecular forces are in hydrofluoric acid, guys?
Hydrogen bonds.
Yep, it's got hydrogen bonding. What else?
Ionic, or it's the ionic dipole, or
Dispersion.
Yeah, dispersion. Hang on, Quenisha's getting here. She's joining. Hold up one second. Okay, hey Quenisha, we just got started. You haven't missed anything. I've been recording. I am right now talking about a chapter 11 connect question that somebody emailed me about. So we're talking about HF and CSI. And so we are listing on HF what types of intermolecular forces exist amongst HF molecules. So I've heard hydrogen bonding, I've heard dispersion forces, and what else?
Dipole.
Dipole, yes, because it's polar. Okay. Now, CSI, that is a special type of compound. And so you would have to catch that. CSI is an ionic compound, isn't it? How do you know if it's ionic?
if it's only sharing one electron.
No.
Oh.
No. It's okay. Y'all just answer. We're learning. We're talking about it together. Hang on.
Is it metal and non-metal?
Yes. Ionic compounds are a cation and an anion, metal, non-metal. I just jumped back to one of our previous slides. Ionic compounds involve electron transfer. So I think, Derek, you might have mentioned sharing one electron. In CSI, in that compound, cesium has a positive charge and iodide has a negative charge. So cesium has actually transferred a single electron to each I so that it would be a negative charge. So in that compound, there has been one electron transferred. But in some ionic compounds, like in magnesium oxide, magnesium has transferred 2 electrons. So it's not always just one. It could be different kinds of numbers.
Okay.
So depending on what the charges are. So CSI is an ionic compound. Therefore, in order for that one to dissolve, we have to overcome ionic forces. Okay. Does that help with that one, Derek, on answer?
Yeah, I just didn't understand because I never saw it in the lecture about like the ionic dipole, and
Yeah.
I think there was one more that I never had seen before.
Right.
So
And we'll kind of hit some of those today a little bit. But when we're talking about hydrogen bonding, dispersion, and dipole-dipole, those forces are used for molecular compounds.
Gotcha.
Like it's a whole other world. So. Okay, now I'm gonna try to pick up where I was. Okay, that's just me looking back to see what I had done. So we had talked about the 3 types of forces. And now we're kind of ready, Derek, this is actually what you were asking, to talk about a different kind of force called an ion-dipole interaction. Oops. Ion-Dipole Interaction. This is not a van der Waals force, okay? So far, what we've really focused on, guys, with the types of forces is really applying them to mixtures. Not to mixtures, but applying them to pure substances. So like just now when I was looking at what kinds of forces exist amongst HF, well, we're looking at if an HF interacts with another HF. So it's a pure substance, right? Pure substances, if you'll recall from Chem 1, can be either pure elements, like something can be pure sodium or pure gold or pure hydrogen. Also, pure substances can be compounds, like pure H2O, or some of y'all in lab, you used pure hexane, etc. And you'll see that chemicals in lab later next Monday for the rest of you. But when we're talking about ion-dipole interactions, these are occurring in a mixture of an ionic compound and a polar substance. Hence, ion-dipole, because the ion part of the interaction comes from the ionic compound, and the dipole part of the interaction comes from a polar substance. And ion-dipole interactions can depend on things like the sizes of the ions and the charges of the ions and the dipole moment of the molecule, etc. But let me show you what I'm talking about. Ion-dipole interactions, y'all, that's what happens when you mix salt and water, table salt. And so y'all know this, you don't have to be in a lab. Does salt dissolve in water? Does table salt dissolve in water?
Yes.
Yeah.
And so think back into Chem 1. Table salt is sodium chloride, right? It's an ionic compound. Do you remember from Chem 1 what happens to ionic compounds when they dissolve in water?
They release
they-
H plus ions.
No, not always.
They disperse or just break up,
Okay, they disperse.
or they become aqueous.
They become aqueous, yeah. They don't always release hydrogen. We're going to get to that later on in Chem 2. I can't tell who's saying stuff, y'all, so just bear with me. I like to know who I'm talking to, but it's not always showing me. Anyway, they disperse. What does that mean as aqueous? Somebody, I think that was Jacob that said like ionic compounds disperse as aqueous. Y'all remember more of the correct lingo for that?
Aqueous just means it'll dissolve in water, doesn't it?
It does mean it dissolved in water. Yes, and what I wrote down kind of what I'm looking for, y'all. I was looking for the word ionizes. So do you guys recall from Chem 1 that like an ionic compound, when it dissolves, if you take a solid and you dissolve it in solution, it dissolves as its ions in solution? Is that looking familiar?
Yes.
Okay. Okay. That's where I was trying to get to. Maybe I wasn't asking the best questions to get y'all there. But it was like we did it with net ionic equations and spectator ions and that kind of stuff. But so any ionic compound, when it dissolves in any solution, it doesn't dissolve, for example, as sodium chloride. What happens to it is it breaks apart, it ionizes into sodium ions, which have a positive charge, for example, and chloride ions, which have a negative charge. So what happens to get this ion-dipole interaction when you put salt in water? See, water is polar. And so the water molecule, it has a partial negative side on it, and it has a partial positive side on it, right? Where those hydrogens are is a positive area, and where those dots are on the oxygen, that's a negative area. And so when sodium chloride dissolves in water, you actually end up with the negative side of the water molecule taking care of the cations, the sodium ions, and the positive side of the water molecule, I say taken care of, but I mean solvating the chloride ions or the negatives. And this is a drawing, a diagram, if you will, of an ion-dipole interaction, showing a cation, sodium, and a chloride ion, an anion, dissolving in a polar substance. And that's the other kind of interaction that we want to talk about. And that, I think, Derek, might be what you meant when you were saying there were some things on the Chapter 11 Connect that we didn't talk about. Is this one? Do you remember seeing that on there?
Oh, yeah, the ion-dipole. Yeah.
Okay. Okay, so that's what it is. Ion-dipole is going to be when you have a mixture of stuff, guys. Ionic compounds and a polar substance will form an ion-dipole interaction. And you'll also recall that not everything will dissolve in water. Remember learning in Chem 1 those solubility rules? And some things will not do this. They will not ionize. Like, for example, barium sulfate was one of them. Barium sulfate, it likes to stay a solid. And what stuff likes to stay a solid and what likes to dissolve, there's lots of things to consider there. We're not going to get into that right now. But so barium sulfate would not dissolve in solution because it's insoluble. Now, we're going to relate some of these physical properties, these intermolecular forces, to different physical properties of solution. And so the first property that I want to talk about of a liquid is something called surface tension. Surface tension is a quantitative measure of the elastic force at the surface of a liquid. And so first off, if we just consider water, guys, if we have a beaker or a glass that's got pure water, we all know, because we use water as the example all the time, we all know that water has dispersion forces. We all know that water has dipole-dipole interactions because it's polar. And we all know that water can hydrogen bond. And something we talked about last time is the hydrogen bonding capabilities of water. There's a lot of them. And so if I could jump back some slides here, because we drew this last time, and if we focus on just this single water molecule here, we can see that each of its hydrogens can hydrogen bond, and both of its lone pairs are capable of hydrogen bonding. So every little part of water is capable of hydrogen bonding. And that can influence some of these physical properties we're going to talk about, because all the things, some molecules, only one little part of them can hydrogen bond, but everything about water can hydrogen bond. That results in water having a rather strong surface tension, a high value. You see evidence of this. Can anybody think of a real life situation or an example? Oh no, I'm gonna run out of time on my meeting. Dadgummit. Y'all, I don't have unlimited Zoom. I only have.
You can launch another one if you need to. My math teacher did that.
We're gonna wrap it up in 10 minutes. I don't have a full license. Okay, maybe I'll quit asking questions and I'll just answer myself. Here we go. Surface tension. Anybody ever done a belly flop in a pool? It hurts.
Yep.
Yeah, it hurts. Why does it hurt? Because the surface tension of water is really strong. That's if you ever go off a high dive, or if you watch high diving. I love to watch that when the Summer Olympics comes on. When they're high diving, y'all, down at the surface of the water, they have a little fountain that's spraying the water, the surface of the water. And part of the reason for that is to help disrupt the surface tension of the water. I mean, another reason that they're spraying it is because you lose, at that height, looking through water, you can lose your depth perception, because the water is so clear. But part of it is to break the surface tension, because if something went wrong in that dive, and I have no idea how high a high dive is, but if you ended up falling wrong, you could really hurt yourself. So we see surface tension when we see those little bugs, the water bugs that walk on water, or those wolf spiders that are always in the pool walking on the water. They've got a little something about the feet of a wolf spider is non-polar, and it allows them to walk on water and not break the surface tension. Usually in class, have y'all ever seen anybody, I do this demonstration, float a paper clip on water? Has anybody ever seen that? If you're really careful putting a paper clip, and I'll show y'all, if you ever want to see some of my magic tricks, just let me know. You can actually float a paper clip on water. Surface tension is the reason why we see that meniscus in water when we put it in a graduated cylinder. Because the meniscus. Because we talked about this in lab, we talked about it a little last week. This is glass, okay? Glass has ions in it. And this is water, and water is polar. And water is polar, so it likes ions. And we saw some things happen in lab this week. Some of y'all get to see it Monday, where the water really seemed to love the glass. And so water loves the glass. It forms this meniscus because of the strong surface tension of this water. It's adhering to the walls, but it's causing that dip in it. Okay? And so what we would say is that the adhesion of the water to the glass is very strong. Okay, adhesion is when you have an attraction between unlike molecules. Okay, and we looked at that a little bit in lab. Another physical property that I want to talk about, I'm going to kind of move through these, I got a timer going, is viscosity. And viscosity is a measure of a fluid's resistance to flow. Okay, and we could see this in our kitchen with syrup, right? Syrup, sometimes we use the term thick. We'll say, oh, that's really thick. Like syrup would be really thick. Corn syrup or golden eagle syrup, they're really thick. But really what we're saying is they're very viscous, okay? And y'all know that viscosity is related to temperature as well. because if you typically, if you increase the temperature, then the viscosity will lower. The viscosity decreases. And viscosity is related to intermolecular forces. You may not realize it because when you look at water, it just looks, it just looks like water. If you compared water to like gasoline, water has all types of intermolecular forces. Gasoline, it's really a mixture of stuff, y'all, but a lot of what's in gasoline is a bunch of this, C8H18, okay? So it's really long carbons, but do you guys see that when I write C8H18, do y'all immediately recognize, oh, that's gonna be nonpolar because it's just a bunch of carbons and hydrogens. And so it's only gonna have dispersion forces. It can't hydrogen bond. It's nonpolar, so there's no dipole-dipole going on. It's just dispersion forces, which are weak, right? Water has got all three. We say this over and over and over. It's got dispersion, dipole, and can hydrogen bond. If you think about it, you can actually imagine the difference in the viscosity of these because gasoline, it splashes really easily, doesn't it? It's real easy for gasoline to splash as opposed to water. Yeah, water still splashes, but I'm telling you by just looking at these two, you can see a difference in how much they splash. And of course, syrup would be another example of something that doesn't splash, but I'm trying to show you the chemical formula of things like gasoline. Okay, the last physical property I want to talk about is vapor pressure. I think this is the last one. Okay. The vapor pressure is the pressure of the vapor at the surface of a liquid. Okay, and so here's an example. If I had a closed bottle and I've got a liquid in this bottle, okay? A pure liquid, doesn't matter what it is. In that bottle, y'all, what is above the bottle is air, okay? But also in that air, there are some particles of this liquid because this liquid is going to evaporate. The pressure of those particles is the vapor pressure. And so you can see evidence of this let's think this liquid is water, for example. And if you have a water bottle in your car with the lid on it, and especially in the summertime here in Mississippi, as the water bottle left in your car, as it heats up, do you guys see that more of this is going to evaporate? And you can see evidence of that when you get back in your car, because if that bottle, even in a house, you can see it, because you start to see like condensation on the inside of it, right? And the longer it sits, the more condensation. Oh. Okay, Brianna, sorry, I'm glad you sent me a message. The more condensation that forms on that bottle. So, as you increase the temperature, you can increase the vapor pressure. Maybe you also have seen evidence of this, like I'm about to lose y'all. I got less than a minute left. And I'm not going to start it back. I'll see you Monday. But let me keep going till it cuts me off. A gas can in your shop. You know how those plastic gas cans in the summertime, they kind of expand a little bit? Gasoline has a really high vapor pressure. And look, it makes sense to us because it only has dispersion forces. So it would have a higher vapor pressure. So weaker forces result in a higher vapor pressure. Stronger forces, like in water, result in a lower vapor pressure, but it's all linked to intermolecular forces.
So as like the liquid or the vapor, its temperature increases, it means like it becomes more excited in the container, and so it like increases pressure?
Yes, becomes more excited. It's called the kinetic molecular theory. Yeah, increased temperature, the molecules move around more. Yes.
Okay.
Okay. It tells me less than a minute. I might not even finish this sentence, guys. I will see y'all virtually Monday for a lecture.
Are we doing lab on Monday?
Group B does lab on Monday.
We might.
Group B. Jacob, you came this past Monday, so you don't do it next Monday.
Okay. What then Wednesday for lab?
No, lab only meets on Monday.